The first thing that we're going to do is give you an awesome definition of Fibre Channel. Fibre Channel is a high-speed serial data transport protocol. The only thing we're using Fibre Channel for is to transport block-level I/O as well as SCSI data and SCSI commands super duper fast between a host and a storage array and vice versa. So Fibre Channel, super duper fast transport protocol. Now, this module is all about Fibre Channel SANs. What's a SAN? Well, a storage area network is just some type of a network that's going to connect our hosts over here to our storage arrays over there. And the main reason we use SANs is to deliver block level I/O. So combining Fibre Channel and SANs together gives us phenomenal performance for the transport of block level data. And the ultimate goal is to take LUNs from that storage array, give them to this host, and then be able to transport that data, as I said, incredibly fast across the links. Now, in the world of Fibre Channel, we actually have three main topologies that we can use to connect my host to my storage array. The first topology that we'll give you a really quick picture of is called DAS, Direct Attached Storage. DAS is also sometimes referred to as a point-to-point topology. What does DAS or point-to-point do? Well, it does exactly what it sounds like. You take a fiber cable and you are going to directly connect that HBA to a front-end port in the storage array. Hopefully you have at least two HBAs for the sake of redundancy, so we can take the other HBA and DAS connect it to a different front-end port for redundancy's sake. Okay? Here what I'm going to do is I'll DAS connect this HBA to this front-end port in this VNX, and then I'll take the other HBA and I will DAS connect it to a different front-end port. So the nice thing about DAS is it's incredibly cheap and it's incredibly simple. You don't need any switch connections or other hardware in the middle. You just need some HBAs on the host, some front-end ports on the array, and you need some fiber cables. Okay? What's great is, as long as you have two connections, you also have redundancy, so we can do failover and load balancing across those connections as well. Now, the biggest problem with DAS is you have limited to no scalability. There's really no growth in the environment. Because this HBA is directly connected to that front-end port, you cannot give this HBA any other connections for better performance and better scalability. And then this front-end port over here is completely dedicated to that one HBA. So what am I starting to see on this array? I'm starting to use up my front-end ports with all these DAS connections. Once I use up all those ports, I can't connect any other servers, which is a big problem. Okay? On lower end or mid-range storage arrays, you have a limited number of front-end ports to begin with. So as you can see down here, I've utilized all of those front-end ports by connecting one host with DAS connections. So you're not sharing your resources very well, and as I said, you're limiting your scalability. Even though our storage arrays support DAS connections, it's not something that we see implemented very often unless the customer has a really small environment with very limited numbers of servers. So let's get rid of those DAS connections. A second Fibre Channel topology that can be used is this thing called FCAL. FCAL. Fibre Channel Arbitrated Loop. Now, an arbitrated loop is really just a fancy name for a shared bandwidth hub. So let's put some hubs into this picture. Now, I've put two Fibre Channel arbitrated loop hubs in this picture because I always want to have redundancy. Now, what is an arbitrated loop hub? Well, it's a physical connectivity device. It's a piece of hardware that has a bunch of Fibre Channel ports on it. Now, in this example, I've given you two really small hubs, a couple of 8-port hubs, just for the sake of time and space. Now, what I'm going to do is I'm going to connect my HBAs to different hubs for the sake of redundancy. This host has two HBAs. I'll connect it to two different ports here. And then from my storage array perspective, if all I have are two front-end ports, well, one will go to this guy and one will go to this guy for redundancy. If I have multiple front-end ports, what I'll do is I'll have half of them connect down here, and then the other half will connect up here. So I've done a nice, smart job of redundantly connecting the host to two different hubs, as well as the storage array ports are connected to two different hubs. So I have some nice redundancy in this picture. Okay. Now, we said a hub is a physical connectivity device. So it allows me to connect all my HBAs and storage ports into these central objects, and now I certainly have better scalability. So if I want this HBA now to see multiple front-end ports, we can now do that via the hub. If I want multiple HBAs connected to this hub to share the same front-end port, we now can do that as well. So I definitely have more connectivity and more scalability. Well, hub technology, fiber channel arbitrated loop technology, even though it's still technically supported, it really is a technology of the past. So 10, 15, 20 years ago, these guys were pretty popular because they gave you better scalability than DAS connections. The downfall or the problem with hubs is its shared bandwidth. We can only have one conversation at a time on that hub, so everyone has to wait their turn in line to send their data. So because of that shared bandwidth, we could have performance issues. And the other big problem with a hub is everybody sees everybody. There is no zoning. There is no real security. So if you're connected to the same hub with another host or other multiple storage ports, every port's going to see every port. It's wide open. There's no way really to restrict that on the hub side. Because of that issue, hub technology, we said, is really kind of a thing of the past, and it's been replaced with this cool new third technology, which really isn't so new anymore, called FCSW. FCSW stands for Fiber Channel Switched Fabric. Fiber Channel Switched Fabric. In a later lesson, you will learn all about different types of switches and fabrics and different terminology. But right now, when we're talking about fiber channel switch fabric, what I've done is let's pretend these are no longer hubs. Let's actually truly pretend these are real fiber channel switches. Now, what's interesting is the picture looks the same as before. A switch itself is actually just a physical connectivity device. It's just a piece of hardware with a bunch of ports. However, what makes a switch different than a hub is it has significantly more built-in intelligence and features. Two of the main features that we'll call out for a fiber channel switch versus an old hub is switches support zoning. Zoning allows us to create isolated or private conversations between any HBA and any front-end port that we so choose. So if I really only wanted this top HBA in blue to see this front-end port only through this top switch, I simply log into the switch with software, I configure zones, and now those guys have private conversations. Okay? If I want this HBA in black through this other redundant switch to only be able to see this front-end port, well, I simply create a different zone over here. Okay? What's fantastic about zoning is you can create whatever fan out and fan in ratios you need. So if I really wanted many, many, many different HBAs from multiple hosts to share the same one front-end port, I can absolutely accomplish that by setting up multiple zones. So many HBAs can share one front-end port. That creates a fan-out ratio. Fan out one port from the array to multiple HBAs. Likewise, if I wanted one HBA to see multiple front-end ports for more pathing, more performance, more redundancy, I could create a fan-in ratio where multiple front-end ports are only zoned to one HBA. So we can create whatever pathing we want, which gives us great flexibility, great scalability, as well as whatever security and paths I need. Okay? Now, in this picture, we're taking a look at two separate one-switch fabrics. Okay? A switch is a piece of hardware, and a fabric, as you'll learn more later, is basically a logical representation of a switch. A fabric could be a single switch by itself, or it could be multiple separate fiber switches that are fiber connected together, treated as one entity. So as of right now, I'm not cabling these two switches together. I'm keeping them separate. So I have two completely redundant switches as well as two completely redundant fabrics that I can do zoning on separately. Okay. Right now, what you're looking at is a nice simple picture of a fiber channel SAN. I have some hosts over here, I have some switches in the middle, and I have some storage over there, and those are the three main components that make up any SAN environment. Okay? If we needed massive scalability, theoretically you can have over 15 million devices in a SAN. I've never counted that high, but that's what the rules say. So you can have a heck of a lot more hosts, a heck of a lot more switches, and a heck of a lot more storage arrays and storage ports if you did need that type of scalability. Okay. So right now, these are 2 switches. Okay? 2 minimum switches required for the sake of redundancy. Okay? What we want to quickly talk about are different types of fiber channel switches. Okay? A fiber switch is classified as either a DS, an ED, or an MP. A departmental switch, an enterprise director, or a multi-purpose or multi-protocol switch. A departmental switch is just a small, cheap switch. Typically, departmental switches have 48 ports or less. So they have less ports, they cost less money, they give you less connections. Okay? It's still a fully functioning fiber channel switch where you have dedicated bandwidth per port and you have the ability to do zoning, but it just gives you less ports, less connections. Now, departmental switches also give you less inherent redundancy than some of the other classifications. So with a DS, you might get redundant power and cooling, but that's pretty much it. Everything else is just on the same blade or the same hardware. So that's where EDs, or enterprise directors, come in. An enterprise director is actually just a bigger, more redundant, more scalable switch. Enterprise directors can have dozens to hundreds of ports. So the more ports you have, the more things you can connect into it. So certainly more scalability, but it's going to cost you a heck of a lot more money. Okay? Now, the added feature of enterprise directors, besides being bigger, is everything in it is redundant. Not only your power and your cooling, but everything else. All of your processor cards, your control modules, your supervisor modules, you name it, it's going to be redundant. So that's what you're also paying for. Okay? Now, a third classification of switches that we'll take a look at in some of the later modules are multi-protocol switches or multi-purpose switches. A multi-purpose or a multi-protocol switch is what it sounds like. It supports multiple protocols. Not only fiber channel, but stuff like iSCSI, FCIP, FCOE, which are all things we'll talk about as the course goes on. So physically, a multi-protocol switch has different blades or modules, some giving you fiber channel ports for SAN connectivity, others giving you Ethernet or 10 gig Ethernet ports so we can start bridging our LAN and our SAN together when required. Okay? It doesn't really matter what kind of these switches you have. As long as you have at least 2 of them, we have redundancy and we have the ability to connect our host and our storage up to do block level I/O. Now, the last thing we're going to talk about is we're going to talk about different port types in our SAN. Allow me to change the color here momentarily. Let's change it to green so it stands out. Something that you will see a lot as we go through these SAN-related modules is you will be familiar with the term N port. Notice I am labeling every HBA and every storage port in this picture as an N or node port. A node port is simply the source or destination of data packets or data frames within our SAN. So all HBAs and all storage ports are simply classified as N or node ports. Okay? Now, every port in the switch also gets a port type or a classification as well. When the ports are completely empty, there's nothing plugged into them, the port is actually referred to as a G or generic port, or sometimes a vendor might call it a U, a universal port. Personally, I think it should be called an unused port, but I have no power, so U stands for universal. Generic and universal ports are just empty ports where nothing is cabled up yet. However, as soon as you plug a node port into that empty port, the switch detects what's plugged into it, and it magically converts that switch port into this thing called an F port. So every single switch port now that has a node port connected into it gets changed to F, which stands for a fabric port. What's essentially happened when you plug a node port into the fabric is it does this thing called a fabric login to uniquely identify itself to the switch and to get acknowledgement that it's truly plugged in. So as soon as that floggy or fabric login occurs, these ports are now marked as fabric ports to prove that that login process has succeeded. Now there is one other port type that we're going to talk about real quickly called an E port. E stands for expansion. Now, if you are going to actually fiber cable two switches together to join them into one logical fabric, whichever switch ports we use for that fiber cable are actually referred to as expansion ports. So in this picture, let's add a port 9 over here, and we'll add a port 9 over here. These are just some new empty ports. If I take a fiber cable and I just physically connect these switches together using port 9 and port 9, well, this port over here will magically become an E port. This port 9 will become an E port. It stands for an expansion port. We're expanding our fabric by merging two switches together, and then we can actually treat these two switches as one big logical entity, one big fabric, and now we can do zoning across that fabric.